Welcome to Unit 3 Stoichiometry Review. So this should be a review from the information we covered in Regents and Honors Chemistry in your previous course. This is meant to be a refresher. You should be familiar with this information when you're done with this review. The first thing we need to talk about is a mole. So a mole is defined as 6.022 times 10 to the 23rd particles. That's all it is, just a number that goes along with that unit of a mole. Just like a dozen means 12, a mole always means 6.022 times 10 to the 23rd. It could mean atoms, it could mean particles, it could mean ions, it could be molecules. Depends on what you're going back and forth with. One of the most important things in stoichiometry is the ability to convert moles into other units. So we're going to talk about how to convert for a single substance and then how to use a balanced equation to go between different substances. But the first thing we need to talk about is how a mole is used in chemical formulas and then how it's used in balanced equations. So the first thing we're going to talk about is how it's used in a chemical formula. Here it's used to represent the ratio between the atoms in a compound. So in our first example down below we have H2O. If you look at H2O, you can see that there's a little 2 down below the H and then your O. That tells me that there are 2 moles of hydrogen atoms for every 1 mole of oxygen atoms in that one compound. When those subscripts change, the number of moles of atoms for that element also changes. In our second example, we have an equation there. Now that is not currently balanced. In order to balance it, you need to put a 2 in front of the H2 and then a 2 in front of the H2O. When that equation is balanced, it now shows that you'll need 2 moles of hydrogen gas to react with 1 mole of oxygen gas to make 2 moles of H2O. That allows us to look at the ratio between those different things in that one equation. That ratio is called a mole ratio, and you use it when you use the balanced equations. Now we're going to go back and talk about a single substance and how you can convert between moles of that single substance and other units. Now moles are great because they allow us to compare things directly, but we don't typically measure things in moles in the lab situation. The most common thing that we measure in the lab is grams. So to convert back and forth between moles and grams, you need to use the GFM, or gram formula mass. To go from moles to mass, you need to multiply by the GFM, and to go from mass back to moles, you need to divide by the GFM. The next thing we're going to talk about is liters. Now liters, you are only allowed to use for gases at STP. Only gases. You cannot use this for solutions. You cannot use this with molarity. Only for gases. To change from moles into liters, you multiply by 22.4, and to go back, you divide by 22.4. The last thing is particles, and this you use Avogadro's number for. To go from moles to particles, you multiply by 6.022 times 10 to the 23rd, and to go back from particles to moles, you divide by 6.022 times 10 to the 23rd. Now this little structure here in this diagram will allow you to go from mass to particles or liters to mass, whatever you want, as long as you go through moles, because you have a conversion factor that will let you do whatever conversion you want as long as you're going through moles. You cannot go directly from liters to particles without going through moles first. Some other calculations for one substance. So the first one we're going to talk about is percent composition. The definition of percent composition is the mass of the part over the mass of the whole times 100. Now the part can be defined as part of a compound, can be part of a mixture, can be part of anything, but as long as it's the part of the whole thing, that's how you use percent composition. The other one is determining the formula of a compound. When we talked about this in our previous course, we described this as an empirical formula. And here you combine the percent composition idea with converting mass into moles to find the ratio of the moles in a compound. Just like we say there are 2 moles of H for every 1 mole of O in water, that works the same for all other compounds as well. There are some examples of this type of calculation found on page 96 through 101 in your textbook, and I have an example problem on the next page. If you have no idea what I'm talking about right now, I would highly recommend you go to your textbook and make sure you look this information over. For our example problem, it says a compound is found to contain 50.05% sulfur and 49.95% oxygen by weight. What is the empirical formula for this compound? So the first thing we need to do is realize that to find the empirical formula, we have to figure out the mole ratio between the 2 elements that are in this compound, between the sulfur and the oxygen. To do that, we need to know how many moles we have. But we can't really do that with percents, so our first goal is to take those percentages and change them into grams. To do that, we assume that there are 100 grams of the compound present. that allows us to say, well, if we have 50.05% of 100 grams being sulfur, then I would know I have 50.05 grams of sulfur. From there, you take those masses of sulfur and oxygen, you change them into moles by using the GFM of those two elements. So for sulfur it's 32.066 and for oxygen it's 16. When you do those divisions, you get 1.5608 moles of sulfur and 3.1212 moles of oxygen. Now those numbers tell us the actual number of moles of sulfur and oxygen in that 100 gram sample. But I want to know the smallest whole number ratio, or the relationship in terms of moles between sulfur and oxygen. To do that, I'm going to look at those numbers and say, okay, if I have 1.56 moles of sulfur and 3.12 moles of oxygen, clearly there's more oxygen than sulfur in there. But what's the relationship there? To look at that, you're going to take those two numbers and divide both of them by the smallest one present. That's the 1.56 number. When you do that, you get 1 mole of sulfur for every 2 moles of oxygen. Once you've figured that out, then you can write your empirical formula as SO2. Here I have a second problem. I'd like you to try this one, so I'm going to let you pause the video. I'll put the answer up in a minute. So it says a compound is found to contain 64.80% carbon, 13.62% hydrogen, and 21.58% oxygen by weight. What is the empirical formula for this compound? So pause this. Try doing that. If you can't remember how, go back to the previous problem, look at the steps there, and I'll put the answer up in a second. So here's your answer, C4H10O. If you're having difficulty with this, again, please go back, look at your textbook, and figure it out. If you're still having trouble, please make sure you ask some questions in class. Alright, the next topic is balancing chemical equations. To balance a chemical equation, you need to use coefficients to make sure that the number of moles of each element is present on both sides of the equation with reactants and products. This again is done so that the law of conservation of mass is followed. And in addition to the normal way of writing an equation, you must be able to show this with particle diagrams. So here we have an example. We have the combustion of methane to make carbon dioxide and water. So the first thing you should ask yourself is this equation balanced? No. If you take a look through, you can see that there's one carbon, but there's 4 hydrogens and then 2 hydrogens. So there's 4 H's on the reactant side, but only 2 on the product side. How do we fix this? To do that, you're going to add a 2 in front of the water. But once you do that, now your oxygens aren't balanced. You have a total of 4 on the product side, so you're going to need to add a 2 to the O2 on the reactant side as well. You can also show this with the diagram. So here you'll see that they give you the CH4, which is the black circle with the 4 white ones attached, and then your 2 molecules of O2 with the red ones. And then you see how they change them up. They mix them back up into their new products. But you'll see there's still 1 black circle, 4 white circles, and then a total of 4 red circles as well. Next thing, types of chemical reactions. There are 4 basic types of reactions that you should be able to recognize and describe. The first one is called synthesis or combination, and you'll see it's the first diagram down below. Here you take 2 separate things to make them into one new product. The 2 separate things can be elements or compounds, depending on what you start with, but you won't need to end with just one single product. Decomposition is essentially the reverse of synthesis. You start with one thing and break up into 2 or more. Again, the 2 separate things can either be elements or compounds, depending on what you started with. The next one is single replacement. In single replacement, you have a compound and you're reacting it with an element, and that element is going to come in and trade places with something in the compound, and one part of your compound will come out as a single element. Now, whether it's the first or second part of the compound that is replaced depends on the identity of the single element, or the C in your equation. If C is a metal, it would be a cationic replacement because metals typically take positive charges, so it will trade places with the A in your compound. If your C is a non-metal, then it will trade places with the B because it's an anion, and it would be called anionic replacement. In the example they've done, that is anionic replacement, so the C must be a non-metal. The last one, double replacement. Here you start with 2 compounds and they both switch partners, but you need to make sure that you end up with neutral compounds. You need to make sure that the charges make sense. So when you write a compound, you typically have the positive thing first and then the negative. So I have my blue and red, so that would be like my A and B, and then C, D. So you'll notice my product, I have A still in the first position, and now it's going to combine with D, which was in the second position in the original reactant. You have to make sure that your positive thing is written first, negative thing written second, and you need a positive and negative in each compound. Other types of reactions, again, combustion, which we'll discuss in class. The acid-base neutralization, which is essentially a double replacement reaction, but always ends up with a salt and water. And reduction oxidation, which again can look like double replacement or single replacement depending, but it needs to show a transfer of electrons. All right, our next thing is using the balanced equation in stoichiometric calculations. So once you've balanced the equation, you can convert from moles of one substance in that equation to moles of another substance in that equation using the mole ratio from the balanced equation. This works again because of the conservation of mass. So here we have our original diagram where you can convert from moles of one substance into mass, liters, or particles, or back into moles. Now, in order to go from substance 1 to substance 2, you have to be in moles. So let's say you start with grams, you have to convert it to moles first. Then using the mole ratio from the balanced equation, you can convert to moles of the other substance. But let's say you don't want moles of the other substance, you want grams or liters or particles. Well, then you can use the same idea and go back and forth with those things using the GFM, or 22.4 liters if it's a gas at SDP, or 6.022 times 10 to the 23rd if you're looking for particles. Here we have an example problem. So I have my combustion of methane again. The question is, how many grams of oxygen are required to completely react with 15 grams of methane, CH4? So you start with your 15 grams of methane. Now, in order to change from one thing into another, I have to get it into moles first. So to do that, I'm going to convert the grams to moles using the GFM of methane, 16.04. Once I'm in moles, now I want to look to my balanced equation to find the ratio between the two things I'm looking at. So I have moles of methane right now. I want to change to moles of oxygen. So I go back to my equation. There are 2 moles of oxygen for every 1 mole of methane. That's why I have that ratio in the second step there. And then my last step is I don't want moles, I want grams of oxygen. So now I need to use the GFM of oxygen to go back to grams. But here I'm going to multiply by the GFM because I'm going from moles into grams. And my final answer would be 59.9 grams of oxygen. So those are the 3 steps you need to take in order to go from grams of one substance to grams of another substance. Okay, other ways you can get mole information other than with liters, grams, or particles. You can use the molarity or molality of solutions because those have moles in their definitions. We're going to talk more about that in class as well. You can also use the ideal gas law, PV equals nRT, because remember N means moles. You can use that to get the number of moles of a gas and work from there. And later in the year we'll talk about pH and pOH and how you can use those pieces of information to get moles of hydrogen and hydroxide. Other calculations that can be done from here. The first one is a limiting reactant. This is the reactant that is consumed first and therefore limits the amounts of products that can be formed. There's also an excess reagent or reactant when you have a limiting reactant, because obviously if you use something else must be left over. And you can use calculations to figure out how much is left over and how much product you are limited to. There's a nice diagram on page 115 in your book that you should look at that shows you how to use particle diagrams to correctly show what a limiting reactant reaction would look like. The other thing is percent yield and theoretical yield. So the amount of product formed when the limiting reactant is completely consumed based on your calculations is called the theoretical yield. This is the ideal amount that should be made if everything is working perfectly. But as you know, in chemistry, things often don't work perfectly. So the amount that you actually make, that you can isolate and then measure, is called the actual yield. And there's a lot of reasons why your actual yield may not match your theoretical yield. The measure of how effective your process is called the percent yield, and that takes your actual yield, divides it by the theoretical yield, and then multiplies it by 100. In class, we're going to do some practice problems with limiting reagent and percent yield, but I wanted you to refresh your memories on what those things were before we got into the math of it. And that's it for Unit 3.